Today we're going to do two things. First, we're going to talk about the difference between empirical versus molecular formulas, really briefly using drawn molecules. And next, most of this is going to be talking about molar volume of a gas at STP and how you use that with the mole. So first, what we're going to do is write the formula, and I'd like you to write the molecular and empirical formula for the following structure. So the next slide is going to have a drawing of a molecule, which hopefully you'll recognize. Okay. So here's the molecule. What I'd like you to do is basically write the molecular and empirical formula for this. Molecular first. So the way you do that, first you have to recognize what atoms are in this molecule. You'll recognize hopefully that there are 3 atoms. There's carbon, there's hydrogen, and there's oxygen. So what we need to do is go through and count each one of those. Do that now. And from that get a molecular formula and then get an empirical formula. Hopefully in doing this you counted 6 carbons. 1, 2, 3, 4, 5, 6 carbons, so it'd be C6, and the other should have had 12 hydrogens and 6 oxygens. Now that's a molecular formula. Remember, the molecular formula is not the reduced formula. You notice all of these are divisible by 6, so if you divide all those by 6, you'll end up with the empirical formula of CH2O. That's why we call the structure, you may recognize C6H12O6 as glucose. Glucose is a type of sugar, and being a type of sugar, I'm not sure where else to go. So if you divide all those, you end up with glucose, which is a carbohydrate, and carbohydrate is a carbon which is hydrated. We see there's a water molecule attached to the carbon, so we call that a carbohydrate. Now the big topic, molar volume of the gas at STP. And how does this have to do with the mole? Well, it has a lot to do with this unit. Well, so far we said 3 things are equal. Now I'm going to tell you that there are 4 things that are equal. 1 mole is equal to 6.02 times 10 to the 23rd Avogadro's number. It's also equal to the mass in the periodic table. And it's also equal to 22.4 liters. Now there's an asterisk there. The asterisk is important for a couple of reasons, and I'm going to talk about those. So this only applies in 2 situations. So 22.4 liters is equal to 1 mole. So it's equal to 1 mole of any gas. These are the 2 situations. It has to be a gas, and that gas has to be at STP. So one situation, it has to be a gas. The second, the gas has to be at STP. STP stands for standard temperature and pressure. You do not need to write these values down. We'll actually use these a lot when we get to the gas chapter. But standard temperature, just for informational purposes, is 0 degrees Celsius, which is 273. Standard pressure is 1 atm, that stands for atmospheres, and 101.3 kPa, kilopascals, 760 millimeters, and hopefully you recognize Hg as being the element, mercury, and then 760 torr. So there's 4 different units for pressure. You don't need to remember or memorize or even write these down. We'll use them a lot, however, when we get to the chapter on gases. So what we're going to do is actually do conversions to volumes and from volumes. So far we've done this. We've gone from moles to mass using the molar mass in the periodic table. And we've gone from moles to molecules. And actually we've also gone from mass directly to molecules as well using the grams and 6.02 times 10 to the 23rd. Okay? But now what we're going to learn to do is this part where we can go from a volume to a moles or moles to a volume. So we're going to use that part of the diagram. I think this is on the back of your calendar. So the amount of a mole of a gas. Moles of gases have very predictable volumes. This is not true for solids or liquids. This is only true for gases. Changing temperatures, hold on for a second. Changing temperature or pressure of a gas can vary the volume. That is why the volume of gas is measured at standard temperature and pressure. Now let's pretend these are all 4 different balloons, and they're all at equal conditions. So that means they have equal volumes, they've got equal pressure, and they've got the equal temperature. So they're all at the same temperature, pressure, and volume. What that would mean is that they would have equal number of moles, which would mean particles. So that's particles. So let's say each one of these was 22.4 liters. We would know there would be 6.02 times 10 to the 23rd molecules or particles each one of these. It doesn't matter if the gas is nitrogen, hydrogen, argon, or methane. Regardless of the gas, they're all going to have the same number of particles. This doesn't matter if it's a light gas like helium or a heavy gas like methane or carbon dioxide. This is true for any gas. So we could say it's true for oxygen, argon, methane, which is CH4, nitrogen, which is most of our air is consumed of, or even a poisonous gas like chlorine, it would be true of. So in summary here, if we have a gas and it's at standard conditions, and we have 22.4 liters, it doesn't matter if it's chlorine or if it's helium, we're going to have Avogadro's number of particles, which means we basically have 1 mole. Now, one thing is different about these two gases. They've got equal number of particles. They've got equal, the number of moles is equal. The volume is equal. There is one thing that's different. Hopefully you recognize that. Has anybody picked out what's different? What would be different? And they've alluded this by the fact that the chlorine balloon is on the ground. Why is a chlorine balloon on the ground? Because they have different masses. Remember, we're always saying the mass in grams from the periodic table. What would be the mass of a mole of helium? Well, all you have to do, if you don't remember, pull out this for your periodic table. Mass of a mole of helium would be 4. So this would be 4.003 grams would be the mass with 4 sig figs of a mole of helium. But if you had a mole of chlorine, it'd be 35.45 times 2. So this would be more than 70 moles. So it's almost 71 grams. That's why this balloon is on the ground, because it's so heavy. It doesn't mean they have the same mass, but they have the same number of particles. They also have a mole. So let's do some problems. Okay, the first one is 22.4 is known as a molar volume of a gas, and it means it has 6.02 times 10 to the 23rd representative particles of the gas. So here's our first example problem. Determine the volume in liters of 0.6 moles of SO2 gas at STP. So we're going to start with 0.6 moles of SO2. Now we want to do a factor label. At the bottom, hopefully you picked, you're going to do this. Moles. At the top, you're going to do liters, but this we're going to do 22.4 liters. Luckily, you're going to see your moles will do this. They'll cancel out. Moles of SO2 is gone. Now we have liters of SO2. So you simply have to multiply 0.6 times 22.4, and you should end up with 13.4 liters of sulfur dioxide. One more sample problem. So assuming STP, how many moles are in 67.2 liters of SO2? Now 67.2, let me see, 22.4, so you know a mole is 22.4. If it's 67, it's got to be quite a bit more than a mole. So we're going to start our number, we're going to start with is 67.2 liters. So we'll write this 67.2 liters, but now we're going to take this factor label like this, and it's going to be turned upside down because we want liters to cancel. So we're going to put liters on the bottom, moles on the top. Liters cancel. And so you're going to divide 67.2 by 22.4 and end up with 3 moles of SO2. So this, it means you have 3 moles or 3 times 22.4 liters as your original volume. Let's do 3 more sample problems. Here are problems. Review more practice problems. Number 1, what volume in liters will 0.68 moles of a certain gas occupy? Number 2, what is a mass of 1.33 milliliters of O2 at STP? And then the last one, how many O2 molecules are there in 1.33 times 10 to the 4th milliliters of oxygen at STP? So let's do the first problem. So there's the answer before we've actually started. So we go back to this problem. What volume in liters will 0.68 moles of a certain gas occupy? You see, I set up so moles is at the bottom. It cancels out. So I'll multiply 0.68 on 22.4 and get 15.2 liters. Let's do the second problem. What is a mass of 1.33 times 10 to the 4th milliliters of O2? So this one involves 2 steps, because what I'm going to have to do first is change milliliters to liters. And I can do that, and then I can use this right here to change liters to mass. So here's the way this problem's set up. Actually, I have 3 steps on this. I first changed milliliters to liters. Then I knew that a liter has 22.4 moles, and I canceled out the liters. And then I wanted to change moles to grams. And since oxygen is diatomic, what I did is I said 1 mole of O2, but I used double the molar mass of O2, which is 16, to get 32. And to get my final answer, you would take 1.33 times 10 to the 4th, divide by 1,000, divide by 22.4, and then multiply by 32, and they give you your final answer of 19.0 grams of O2. One more problem. How many O2 molecules are in 1.33 times 10 to the 4th milliliters of O2 at STP? I'm going to pause and let you do that problem. So you should start with the 1.33 times 10 to the 4th milliliters, change that to liters just like last time, and then your last step is going to be a little bit different. Now here's what I did. So I changed milliliters to liters, and then I knew a liter contained 22.4 liters is 1 mole. But instead of a mole this time, I went ahead and put 6.02 times 10 to the 23rd molecules at the top. And that gave me the number that I put at the top. And so what I do now is I multiply the 1.33 times 10 to the 4th divided by 1,000 times 6.02 times 10 to the 23rd, and then divided by 22.4, and that gives me the final answer of 3.57 times 10 to the 23rd molecules of O2. Notice on the last problem, prior problem, I could have actually, if I wanted to, since the moles of O2 cancel out, I could have said 22.4 liters, since it's a gas, is 32 grams, and put that there and save 1 step, similar to what I did in the last problem. So we'll be working on some problems like that this week. This is one of the last types of problems we'll have for this chapter. Good luck.